Now that you've learned about different techniques to design your system, how do you make sure that the system you've created is correct? There are many ways that you could verify that your system is working the way you intended. For example, you can run tests and see if the actual behavior matches what you expect. One technique you'll learn about here is called model checking. Model checking is a systematic check of your system's state model in all its possible states. Basically, you check all the various states of your software and find if there are any errors by simulating different events that would change the states and variables of your software. So, you check if the state model of your software contains some flaw. These checks are done using model checking software. Let's ask an expert about the different types of model checking software that is used today in the software industry.
Before we talk about model checking, it's probably a good idea to talk about the whole process of specifying and testing and reasoning about systems, because that's what we all do. When we build something for you, we're doing some very, very complicated mental reasoning that the sentences that we're writing in some programming language are actually going to deliver the product that you want to make, for your business. Right? The sheer amount of complex reasoning that we do it so automatically we don't realize how complicated it is. But anyone who's ever taught introductory programming to students who, the first time they see a for loop, they simply can't understand what it does. They don't understand how to make the for loop do what they want it to do, because they haven't built the internal structures for reasoning about a for loop. Now, what we try and talk about is, what varies over the time, every time you go through the for loop, what is it you're trying to change, what's the kind of progress you're making. These are all English language attempts to sort of say, yes, a for loop's an iterative solution to a particular problem, and then you wonder 5 years later why you ever thought a for loop was mysterious, because you now internalized all the reasoning that you need to do to write a for loop. In a complicated system, you're also doing this internalized reasoning, but it's now becoming less certain. As an experienced programmer, I can look at a for loop and quickly say, yep, I think I know what it's doing. But now if I've got 5 different applications, they're all talking to a bunch of web services, and the web services are talking among themselves, and I've got database updates going on, and there's a whole flurry of things acting concurrently. It's not so obvious anymore whether simple properties for the system are holding, such as a piece of data is actually consistent or not. How do you reason about a system like that? We build them. We rely on things like the database to ensure transaction atomicity. But how did the database guys convince themselves that, yes, their database actually does preserve atomic transactions? How do you reason about these complicated systems? Well, this has been a problem, again, identified in the 70s of what's the best way to reason about your programs. And there's been 2 schools of thought. Not competing, they're complementary schools of thought. One school of thought says that, well, we can look at our program as a mathematical artifact, and we can prove properties about what the program does, assuming that we have a good enough understanding of the behavior of the programming language. It's so-called semantics. And that's a very successful approach for a whole range of systems. And in fact, I've proven programs correct using this technique that are deep down inside production systems where a failure wouldn't be at all obvious until much later. And that works. It's a perfectly good technique, and it's actually an important part of your toolkit. But there's other kinds of problems, such as concurrent activities of programs communicating to each other and updating shared data, where a handwritten proof type approach doesn't work, because you're not dealing with generalized things, you're dealing with a large number of really special cases. What if you do this, then I do this, then you do that, and I do that? And it's very hard to, by hand, anticipate all these special cases. And in fact, there are famous papers in the literature where they prove a certain protocol is correct, and it turns out that the proof has got a subtle bug in it. So there's another line of approach which says, okay, for these things that have all these weird special cases, what we should do is mechanically enumerate all the special cases. What does that mean? Well, I have a system. It's got some state. When it does things, it changes from one state to another state. I can express the behavior of that system as state changes. And I can say things like, it'll never be the case that the total debits and total credits in this account don't balance. Because statements about the total debits that have occurred, the total credits, and the current balance, those are all statements about state. I can then try and express things like saying, it's never the case that I will sell 2 tickets. It's never the case that I will sell the same ticket to 2 different customers. Important airline reservation specification. So that's a statement, again, about a state. You're saying that before this ticket was sold, the world was in a certain state. After this ticket was sold, the world is in another state. And this other state doesn't have 2 people holding the same ticket. If you can express your problem that way, then you can do what's called model checking. And model checking is a technique that does state exploration. It says, given that you start in this current state, explore all the possible ways you can go into the future and reason about what all those possible future states can look like. Going back to the ticket thing, I might make a statement that says along the lines of, if at some point in time ticket A is sold, then at all future states in time, ticket A is only held by exactly one owner. The model checker can then look at the way the state system evolves. How does it know that? Well, the model checker has a little bit of an idea of how your program runs. That's a different issue. We'll get to that. But the model checker explores the future, and then it comes back with an answer. And the answer is either, yep, it's never the case that 2 people have purchased the same ticket, or it says, that's wrong. And here's the counterexample. Here's all the weird steps that the system went through in order to make it so that customer 1 and 2 both hold onto the same ticket. The model checker then actually, it doesn't only tell you that you're wrong. It says, and here's one example where you're wrong. The problem with model checking is the so-called state space explosion. If I've got 1 bit, I have 2 states. If I've got 10 bits, I've got 2 to the 10th states. If I've got 1 million bits, I have 2 to the 1 million states. There's no way to explore 2 to the 1 million. Current model checkers, last time I knew anything about them, were about 2 to the 40th states was about the most you could explore. That means if your problem can't be described in a small number of bits, you're in trouble because a model checker won't help you. So what model checking relies on is the ability for you to take your piece of code and extract from your piece of code just those parts of the problem that you need to model. So you might not be able to model, for example, in a purchasing system, you might not be able to model the totals on the purchase orders because that's lots of bits. You might not be able to model a lot of items on a purchase order. But you might be able to model that there's 1 or 2 items on the purchase order because that's all you care about, because what you're trying to prove is that if you ever make a request of the fulfillment system to actually get the order paid, that all of the orders on the order actually have made it to the shipping state. So model checking relies on this thing that we call the small world assumption, that if you have a system and things are going to go wrong, they're going to go wrong in small cases. And that if you look at the small cases, you can convince yourself to a reasonable degree of confidence that it's probably going to work in the big cases. That's the program extraction part. That's still a big problem. No one knows how to do that well. There's lots of tools that are good partial solutions, but there's no general solutions to that. Model checking and reasoning about programs and agile development and test cases, they all fit together very nicely. Because if you can specify what your system does, you can write tests for it. In some sense, tests are themselves specifications. Because if you pass it, it's doing the right thing. If you don't pass it, it's doing the wrong thing. If you can model check your system, that's good because it means that you have some specifications that don't need test cases, okay? Because the system is actually correct. Or you can think of it slightly differently. If you model check and you get a counterexample, that becomes a new test case. You throw that into your test suite, and then when you fix it and run it the second time, that test better fail. So they're really all the same thing, just with different mathematical technologies behind them. It's only a small percentage of all the code that's written that can actually benefit from model checking, because either it's not important enough and you don't care to do the investment, or it's simply too complicated and model checking is not powerful enough yet.
Think of model checking like going through airport security. Security guards in airports know the rules of what people should have or shouldn't have to get on an airplane. They don't make any exceptions. Model checking is similar in that it checks the behavior in the state model for your system and notifies you of any violations to the rules. A rule that your software is required to satisfy is that it must not produce a deadlock. A deadlock is a situation where your system cannot continue because two tasks are waiting for the same resource. Your model checker would simulate the different states that could occur in your system, and if a deadlock is possible, it would provide details of the violation. Now, how do you model check your software? Model checkers generate a state model from your code. A state model is an abstract state machine that can be in one of various states. The model checker then checks that the state model conforms to certain behavioral properties. For example, the model checker can examine the state model for flaws like race conditions, exploring all the possible states of your model. There are 3 different phases to performing model checking: the modeling phase, the running phase, and the analysis phase. The modeling phase comes first. This is where you enter the model description. This would be provided in whatever programming language your system uses. You also describe the desired properties. During the modeling phase, you can perform some sanity checks. These are quick checks that should be easy to do because they usually come from very clear and simple logic. It's like testing if a light bulb is working by flipping a switch on and off. It's clear to see when the light bulb is malfunctioning. It's beneficial to get rid of these simpler errors before using any model checkers, so that you can focus on specifying the more complex properties to check. The second phase is the running phase. This is when you run the model checker to see how your model conforms to the desired properties that you wrote in the modeling phase. The last phase is the analysis phase. This is where you check if all the desired properties are satisfied, and if any are violated. Violations are called counterexamples. Your model checker will provide descriptions of violations in your system so that you can analyze how it got to that state. Using the information from the model checker, you revise your software to fix any problems, then run through the phases again. You do this until you can be sure that your software is correct with respect to the desired properties. Model checking is a very useful verification technique. There are many ways to test your system's behavior, like unit testing, beta testing, and simulations, but model checking can help find errors that these tests can't. If you're looking to use model checkers to develop your programs, there are many different free model checkers available for developers that use different languages. Model checking is now another technique that you can use to make sure that you are not only creating well-designed software, but software that meets desired properties and behavior. Using model checking after you've used the design techniques you've learned in this course will ensure that your software is behaving the way you intended.
Congratulations! You completed all the video content for this first course. Next up are the remaining capstone assignments. So far in the capstone assignments, you've been documenting the software in various UML diagrams. Now we're going to flip things around. You're going to take a change expressed in a diagram and apply that change to the code for a real software product. That will be followed by an end-of-course quiz that will test your knowledge from all of the material that we covered in this course. See you next time.